In 1843, German amateur astronomer Heinrich Schwab published a modest 27-page paper in Astronomische Nachrichten revealing a rhythmic 11-year fluctuation in sunspots, a periodicity that Scottish physicist John Napier and later Rudolf Wolff traced backward using archival records to 1610, when Galileo Galilei first trained his telescope on the solar disk. You will discover how tree-ring radiocarbon anomalies prove this 400-year Eddy Minimum cycle, why the current cycle 25 is outpacing NASA predictions by 40%, and what actually happened to telegraph systems during the 1859 Carrington event. To understand the ticking clock inside our G-type main sequence star, researchers at the National Solar Observatory point to tachocline shear layers located 200,000 kilometers beneath the photosphere. Within this turbulent boundary zone, differential rotation shears primordial plasma, generating the powerful magnetic fields that drive the solar dynamo described by the Babcock-Layton model.
The Sun remembers its own history through frozen isotopes locked in polar ice.
By extracting ice cores from Greenland and Antarctica, glaciologists measure beryllium-10 and carbon-14 fallout rates that correlate directly with historical cosmic ray fluxes modulated by solar wind strength. These isotopic proxies reveal grand solar minima, periods of prolonged suppression such as the Maunder minimum spanning from 1645 to 1715, when telescopic observers recorded virtually zero sunspots for decades. During that 70-year freeze, the Thames River in London regularly froze solid enough to host frost fairs, while global temperatures dropped by an estimated 0.5 to 1.0 degrees Celsius. Complementing the Maunder minimum, the Sporer minimum from 1450 to 1550 and the Wolf minimum around 1300 demonstrate that this pacing operates on a centuries-long macrocycle. That macrocycle is precisely what researchers call the 400-year Siesta-Vries cycle, driven by long-term oscillations in solar interior dynamics and planetary tidal forces.
We are watching a stellar heartbeat synchronize with planetary gravity fields.
Fast forward to the present day, where Solar Cycle 25 officially commenced in December 2019, managed jointly by the NOAA Solar Cycle Prediction Panel and NASA scientists. Initially, official forecasts predicted a subdued peak of roughly 115 sunspots, mirroring the weak activity of the preceding Cycle 24. Instead, as recorded by the Solar Influences Data Analysis Center in Belgium, the Sun shattered those projections by consistently producing over 200 sunspots per month throughout late 2023 and 2024. This unexpected surge led the prediction panel to officially revise the expected peak window to between January and October 2024, accelerating the countdown to maximum magnetic stress. When magnetic field lines in the corona cross and reconnect, they release up to $10 25 joules of energy in minutes, accelerating protons to relativistic speeds. These outbursts are classified by the Space Weather Prediction Center from C-class up to catastrophic X-class flares, which instantly ionize Earth's D-layer ionosphere. On September 1, 1859, British astronomer Richard Carrington witnessed a blinding white light solar flare while projecting sunspots through a brass telescope. Within 17 hours of Carrington's observation, a coronal mass ejection slammed into Earth, traveling at an unprecedented speed of over 2,000 kilometers per second.
Telegraph operators reported receiving messages with their batteries completely disconnected as induced currents powered the lines.
Auroras were visible as far south as Cuba, Hawaii, and Santiago de Chile, while gold miners in the Rocky Mountains woke up and cooked breakfast at 1 a.m. under crimson skies. If a Carrington-class storm struck today, a comprehensive 2008 study by the National Academy of Sciences estimated economic damages exceeding $2 trillion within the first year. Modern society relies heavily on low Earth orbit constellations, where Starlink and hundreds of other satellites face severe orbital decay during solar maxima due to atmospheric heating. When extreme ultraviolet radiation heats the thermosphere, atmospheric density at 400 km altitude increases by orders of magnitude, generating aerodynamic drag that deorbits unprotected hardware. In February 2022, SpaceX lost 40 out of 49 recently launched Starlink satellites when a moderate G1 to G2 geomagnetic storm increased atmospheric drag by 50%. Power grids are equally exposed. Long-distance high-voltage transmission lines act as giant antennas for geomagnetically induced currents that can melt multi-ton transformer cores. This exact failure occurred on March 13, 1989, when a severe geomagnetic storm caused the Hydro-Quebec power grid to collapse in just 92 seconds, leaving 6 million people without electricity. To monitor these threats in real time, NASA and the European Space Agency maintain the SOHO and Solar Orbiter spacecraft stationed at the L1 Lagrangian point 1.5 million kilometers sunward. These Sentinel instruments measure solar wind velocity, interplanetary magnetic field orientation, and coronal mass ejection trajectories before impacts strike our geomagnetic shield. As Cycle 25 reaches its apex and transitions toward the descending phase, the solar dynamo continues its relentless, multi-century march toward the next grand minimum predicted for the 22nd century. Every cycle reshapes the heliosphere, scrubbing the interstellar medium and leaving permanent chemical markers in the geological strata of our changing planet. We remain tethered to a variable star whose ancient rhythm was ticking long before humanity learned to read the sky.